Hello, this is our Data 222 presentation on the effect of population on electricity and heat usage. We can introduce the presentation by saying that we chose to evaluate the Chicago energy usage data set that recorded the energy usage in 2010 for each building in the Chicago area. In addition to the energy usage that it gave within the data set, it gave many categorical variables for each of the buildings, such as building type and other signifying behaviors of the building. In evaluating the data, we found that it was largely numerical variables with variations of kWh and therm data, which are electricity and heat data usage for the buildings. We chose as our response variables, in seeing the large number of numerical variables centered around kWh and therm, we decided that we would use these as response variables and evaluate the mean of both of these variables for the year, as it would give an overall look of the year in heat and electricity usage, both working towards explaining energy usage for each building. For the explanatory variable, we believed a large predictor in the variation of the kWh and therm would be the total population of the building. So we wanted to evaluate the total population's effect on kWh and therm. Our research questions we used to address this is, does the total population of a Chicago building in 2010 affect the amount of heat used? And does the total population of a Chicago building in 2010 affect the amount of electricity used? Our hypotheses in answering these research questions were there is a positive linear correlation between total population and electricity usage in any given building, as well as there is a positive linear correlation between total population and heat usage in any given building.
So the first step we had to do was go through the data cleaning process. It's important to clean data because it removes outliers and any missing cells, making the data usable and more readable. So first, in order to clean the data, we used complete.cases to remove any rows with empty cells. It returns a Boolean vector whose values represent whether or not a row has any missing values. Then using our indexing rules, we can create a new data frame containing only the rows without missing values. And then the second thing we did was we removed any outliers in our columns of interest of the data frame. And we are able to do this by writing code that checks each row for outliers in the columns of interest and removing the rows that do have outliers. By doing this, we ensure that we will generate accurate models to display our data and make accurate observations of our data. So here's the code. This first here is just our function definition for determining outliers. And then this is how we used complete.cases to remove any rows with missing values. And then this is the code that uses our outlier function definition to remove outlier rows from our columns of interest.
So after we cleaned the data, we first ran a regression on our two different hypotheses. This is our first one on total population affecting heat usage. And as you can see from the scatter plot, the data was very centered early on through the first 0 to 100 data points. And there were some other ones that kind of went to that the population was very high. Our conclusion from this regression is that our R squared was 0.04294, which means that it only explains about 4.3% of the variability. That total population only explains about 4.3% of the total variability of heat usage. This is obviously very low, and it tells us there's probably a lot of other factors that also explain heat usage outside of total population. However, our p-value was significant for total population at 2e to the minus 16, which is approaching 0. So it does mean that total population is statistically significant as a predictor of heat usage, which means that it is not likely that the variability explained by our regression is due from random chance. It's most likely what it is. And overall, we can conclude that it is statistically important, but it is not practically important, as it only explains about 4.3% of our variation. Similarly, for our next chart on total population affecting energy usage, the graph looks very similar, and it is very similar in the fact that our R squared is low at only 0.02733, or about 2.7% of the variation explained by the model. Again, this is low, but also our p-value is also still low at 2e to the minus 16, which is approaching 0, which similarly means that it is again statistically important and is not due to random chance, but our model is not practically important as it explains very little of the variability. It probably means that there's a lot of other factors that affect energy usage, and total population is not one of them, or is one of them, but just not a very large amount. Then after we did our regression, we decided for our further analysis to use a decision tree for each of the models. Firstly, for heat usage. In this first decision tree, we can see that the population is considered low if it is under 62, and is considered high if it is greater or equal to 62. So basically, if the population is less than 62, it is more likely to have low heat usage according to the decision tree, while if the population is above 62, it is more likely to have a high heat usage. The prediction is not very confident in either branch though, as for the higher branch, only 40% are considered high when they are above the population threshold, and for the lower one, only 60% are considered low if they are below the threshold. So basically this means that similarly to our linear regression, it shows that total population is not largely affecting the heat usage, and there's probably a lot of other variables that would also assist in predicting that. Yeah. And then decision tree for electricity usage is very similar. In this case, the threshold for a high was total population of greater than or equal to 77, while below would be lower than 77. Thus, when the population is greater than 77, the electricity usage is considered high. However, only 41% are considered high when this is true, thus it is not strongly predictive. As for the right branch, when the population is less than 77, it is considered low. Again, in this case, only 56% are low users, and this is not a very accurate predictor as well. Similarly, this means that there's probably a lot of other variables that would predict electricity usage, and while total population is still significant, it's probably not the best predictor of electricity usage.
Yeah, so moving on, our answers to our research questions. So overall, the population does significantly predict the amount of electricity and or heat used in a building. This proves our hypothesis that a higher population in a building would predict a higher amount of energy usage. So problems and solutions in our research, as we previously mentioned, our first problem was missing data in our research. So like a lot of the data set had rows of missing values, which could skew the results or make statistical analysis invalid. And our solution was to use the complete.cases function. Our second problem was the outliers in the data set. The outliers in electricity and heat usage could distort the results, so we use our written code, the is_outlier, to identify and remove them. So some of our challenges and limitations to the data set are that the data set only covers energy usage for 1 year. There's also factors like energy efficiency that were not included, and it also doesn't account for changes in population patterns or weather variation. So some of our ideas for future investigation include, is there a correlation between the amount of electricity and heat used in the same building? And then also, is there a correlation between the building type and amount of electricity or heat used? And in conclusion, we believe that population will have a much more significant impact on energy usage, but there is not a large correlation between population and heat or electricity usage at all.
Thank you for listening.